All right, so for example, if I have a spring here, and if I stretch it, it's going to exert a force on the object. So let's say that this is my equilibrium position, x equals 0, and I stretched it by a distance x, then the force on the spring is going to be in this direction, right? Like I pull a spring down, it's going to tend to go back towards the equilibrium position. And Hooke's law just says that this force is proportional to the elongation, or the compression as it may be, times k, where k is the spring constant. The spring constant is just something that we determine experimentally. You'll do this in the lab, actually. You just put a mass, or you apply a force to a spring, measure the amount of displacement, or the amount of elongation that it causes, and then divide those two numbers. Divide the force by the displacement. And that'll give you k, which is just the spring constant. It's measured in newtons per meter. In Hooke's law, we also have a sign here that F is equal to negative kx. And the reason that is because the direction of the force is always opposite the direction of the displacement. So if I pull a spring in one direction, the force is going to be the opposite direction. If you've ever played with a spring, you know that's true, right? That the force is always opposite the direction that you pull it. All right. So for example here, sort of the same, but if this is my equilibrium position, and then I have a mass attached to the spring, I pull it back, the force on the spring is in this direction. So the force on the spring is always opposite the displacement, and so the spring sort of wants, the spring doesn't want anything, right, because it's just a spring, but it wants to return to its equilibrium position. Which is at x equals 0. So if I compress it the other way, the force will be the opposite direction. Oh shoot, I don't have this clip, I'm sorry. It was just a clip about Robert Hooke, who came up with Hooke's law. I think we sometimes forget that, in the 18th century, the 1700s, that was really the birth of modern science. And it really started with Isaac Newton and a lot of the other scientists that lived in that time. So they were all big names, right? Like Isaac Newton, Robert Hooke, who you might not have heard of before now, but you've heard of Robert Boyle, right? Of Boyle's law, right? From the ideal gas law. And a lot of other scientists that were all part of the Royal Society in Britain. But this clip, which I don't have, I'm sorry, but it was just about sort of their personalities and how they conflicted. Apparently Newton he was kind of an ass towards everybody else, so I'll try to remember to bring it next time. All right, we're going to apply the conservation of energy. That is that the initial energy equals the final energy in a similar way as we did for gravitational potential energy, but now we're going to apply it to elastic potential energy. So remember, gravitational potential energy said if I have an object and I put it in a certain position, it has the potential for motion. Well, in a similar way, if I put something on a spring and I stretch the spring, it has the potential for motion as well. And we'll derive what that expression is, but let me just go and give it to you. The potential energy, this is the elastic potential energy. This is just the energy of a spring, is equal to 1/2 k times x squared, where again, this is the spring constant. And x is just the compression or the elongation or the displacement of the spring. All right, so say for example I had this this object. Let's put some numbers in just for an example. Let's say that the mass of this object is equal to 2 kilograms. All right. Initially, it has no elastic potential energy, and it has no kinetic energy because it's not compressing the spring and it's not moving. And then I cause it to compress the spring. So it's like one of those little pullback car toys where they compress the spring. That's what I've done here, is I basically compress the spring and push the block up next to the spring. let's say that x is equal to, I don't know, 10 centimeters, which you know is 0.1 meter. And let's say that the K value, the spring constant, is 1,000 newtons per meter. Right. And then the spring releases all of its energy into the block. At this point, it's like the spring isn't even there. The spring basically returns to its equilibrium position, and it releases the block. And I want to know what is the velocity of the block. So I can set this up just like we did for conservation of energy, and that is that the initial energy equals the final energy. The initial energy is all caught up in what type of energy? It's all in potential energy. And the final energy is all in what? It's all kinetic energy. So there is no kinetic energy initially, and there is no potential energy initially. So I just say the elastic potential energy initially equals the final kinetic energy. So that's 1/2 kx squared equals 1/2 mv squared. My halves cancel. That's 1,000 times 0.1 squared. That's my kx squared divided by m, which is what, 2 kilograms? Yeah, 2 kilograms. Square root of that, that's what, 10 over 2, 5, square root of 5. So approximately 2 meters per second. 2.2? Yeah, okay. Those work out just the same way as the gravitational potential energy problems. The only difference is now instead of doing mgh, you're doing 1/2 kx squared. All right. If you had one like this, you probably wouldn't have a gravitational potential energy problem. Or you might have one that's combined, where you have both gravitational and elastic potential energy. All right, now the real purpose of this section, though, for bringing up springs, is to talk about forces that are positionally dependent and how to find the work done by those forces. And a positionally dependent force is like a spring, right? It depends how long you've compressed the spring or how long you've elongated the spring to find the force. So if we want to find the force, remember work by definition is equal to force times displacement. We'll assume that the force and the displacement are in the same direction, so I'm just going to leave off that cosine theta term. But here I have a force that's dependent upon x. So my force is a function of x. So I can do something where I take the integral. So I'm going to say the work is equal to the integral of the force times the differential element dx. Let me rewrite this up here just so you're not confused. Let me just, I'll scratch that. I'm just going to write it as F times X. Right, so if I want to find the work of a force, I can multiply it times the X distance. All right, but sometimes I might have forces that are dependent upon X. So I might have a force, and as I'm compressing a spring, for example, that force is actually going to increase. So F isn't a constant value. F is going to change depending upon the value for X. Go with me on that? That is, I have a spring and I compress it, my force isn't constant, right? I have to increase my force the more and more I compress my spring. Right, so I can't just say, well, it's the product of the force times x, because I don't know what the force is. The force changes. Yes, with me? All right, so in order to calculate that, I do a summation. And a summation is just an integral that for every step, when I compress this spring, all right, as I compress this spring, I take the product of F times X for every step. All right, so I compress the spring just a little bit, and I say, what was my force? And I multiply it times my elongation. Then I compress it just a little bit more, and I say, what is F times X? And a little bit more, and a little bit more. And each time I take that product of F times X, I add it up. So what is an integral then? what does an integral do? When I take an integral, what does that do? It is what? No, you're thinking derivatives give you the rate of change, and that's correct. An integral, y'all haven't gotten integrals yet, have you? Okay, an integral is defined as a summation, right? It's a summation of one number times another number, basically. We saw this when we were doing kinematics graphs. Remember we did v versus t graphs? And we said that the area under that graph is the same as an integral. Like the area under the graph is the integral of v times dt, right? And so that's the same thing here. It's like we're plotting f versus x. As x increases, f increases. And so when I take the product of f times x, or when I take rather the integral of f times x, I'm taking the area under this graph. And the area under that graph is the work done. All right? So I can put in my function for f. It's going to be the integral of k times x. I'm just going to put in the magnitude of f and not worry about the direction. K times x times dx. And remember, when we're taking the integral of a polynomial, the integral of a t to the n dt is a t to the n plus 1 over n plus 1. And so what is going to be the integral of kx dx? This will be the same as k integral x dx. What's the integral of x dx? It's like x to the 1. What is it?
X over 2 squared.
Right, x squared over 2. So it's the same as k times x to the 1 plus 1 over 1 plus 1. Where here I'm just letting n equal 1. If I rewrite that as 1/2 k x squared. So that's the work done to compress a spring over a distance x. And that's also the elastic potential energy. Because any work that you put into that spring, you'll convert into potential energy. That, of course, is assuming what? Or maybe not, of course, but like we did a similar thing here where we said the work done on an object in a gravitational field is equal to its potential energy, and we assumed what type of forces were at play. Conservative forces, right? So we were assuming that there was no energy loss to friction or deformation or any of that. And that might not be exactly true here, but it's pretty darn close to true. That you're not losing energy to heat or sound or deforming of the metal, even though the metal is actually stretching. All right, we'll work through some examples where this comes into play. I know this might be a little new to you. Sorry, that's where I was going to do the thing. So our work is equal to 1/2 kx squared, and the elastic potential energy is equal to that. So my elastic potential energy is equal to 1/2 kx squared. I say it's equal to the negative of the work of the spring, because remember our force was actually negative kx, so this works out to be negative 1/2 kx squared. Don't sweat that right now, it's not important. All right, so our elastic potential energy is just 1/2 kx squared.
Should there be an S underneath that, or is it just...
Yeah, that's our potential energy of the spring. And it's different from the gravitational potential energy. All right. Why don't y'all try this quick test, and then we'll try some more difficult problems. Let's go ahead and try this one. Remember, this works out exactly the same as gravitational potential energy, the conservation of energy problems, except now instead of doing NGH, we're doing 1/2 kx squared for our elastic potential energy. sure you convert your X to meters for SI units. Remember that you are welcome to work together if you like. Stop at 250. 250. Pretty sure B is the right answer. Let's work through it. So here I just have elastic potential energy, and over here where the X is 0, I'm just going to have kinetic energy. So my elastic potential energy will equal my kinetic energy. That's 1/2 kx squared equals 1/2 mv squared. And then it's just a matter of solving for V. K is 1200. X is 0.2 meters squared divided by the mass, which is 1. Is that 6.9? I think it is. Is that right? And how do you get 48? I forget how you get that.
You don't square root of 48.
Oh, you don't square root it. Okay, yeah. So, yeah, 6.9 squared is 48. Yeah, so if you didn't square root that, you get 48. But it's 6.9 meters per second. All right. That's pretty basic, right? Do that no problem? Yeah. Let's do a more complicated problem where we actually have some dissipative forces involved. All right, so here you're going to kick a block, so its initial velocity is 12 meters per second, and then the block has a mass of 3.2 kilograms. The block slides on a surface where the frictional force varies with position, and that function is given here. The function is F equals 3x cubed in the I direction. All right, so it's actually in the negative I direction. Okay, so you can think of this as like a frictional force, if you will, if you want to, but it's just sort of a force. But that force is going to be in this direction, opposite the motion. All right, so first let's just find what is the initial energy of the block. What does the energy consist of? What type of energy? It's all kinetic, right? So first, just what is the initial energy of the block? And I'm going to give you a hint on the next part. Just a second. Did I get it?
It's 230.
That's what I got too. So 1/2 mv squared. That's equal to 1/2 of the mass, which is 3.2 kilograms, times v, which is 12 meters per second, squared. That's 230 joules. All right, so that's the total energy of the block. And now I want to know how far does the block slide before coming to rest. Now, this kinetic energy, in order for it to come to rest, you have to do that amount of work. All right, so that force F has to do that amount of work, 230 joules of work, to cause the block to come to rest. It has to take away all that energy. All right, so what you want to do is you want to say that our work is equal to the integral of our force times dx, and you know that has to equal 230 joules. Actually, that has to equal negative 230 joules. To try that out, you want to take the integral of that force function and solve it so that it's equal to 230 joules. Solve for xf. First step is just take the integral of f dx, where f is negative 3x cubed. You get a number? 3.14? You get 4.2. Right, let's see. What's the integral of 3x cubed?
Negative 3 divided by 4 times x cubed b.
Right, so
times x.
negative 3, that's just a constant, it can come out, times x to the 3 plus 1 over 3 plus 1. Right, remember our integral of a polynomial, x to the n plus 1 over n plus 1, equals negative 230. I'm going to apply some limits to this. Have we talked about limits of integrals? I don't know that we have we? Okay, well when you take an integral, you can apply limits to that integral, and you can say that this applies over x, like for example here, I take my limit to be from 0 to x over f. Those are just my initial and final positions in this case. What are your initial and final conditions for that? And what that means is is that I'm going to, let me rewrite this interval. I'm going to apply those limits from 0 to xf, and it's going to look like this: negative 3 times xf to the 4th over 4 minus negative 3 times 0 to the 4th over 4. Alright, so I'm just saying this, plugging in xf for my final condition minus my initial condition. This term goes to what? That term goes to 0, because 0 to the 4th is just 0. So that term goes away, and then that's equal to negative 230. You with me on that? I know many of you have had calculus in high school, but this might be new to some of you. Okay? Very likely to have to do an integral on this test. I don't know, 80% chance on this quiz that you have to do an integral like this. Likely to be paired up with a more complicated problem.
Did you solve it out?
Yeah, of course I'm back. Yeah, so if I'm going to solve this now for xf, I'll just go and get rid of these negative signs, and I get 3x to the 4th, and I'll come up here, 3xf to the 4th over 4 equals 230. And so xf to the 4th equals 4/3 230. It's 307. And then I raise both of these to the quarter power. I get 4.2. What several of you said. All right. There are a couple of homework questions that are similar to this, and if you look back at old tests, you'll find questions that are similar but different. All right. One more little topic here. It's just sort of an afterthought, really. We okay with this, though? You'll get some more practice in the homework. So if it doesn't click just yet, don't sweat it too much. All right. Then I go down. One more thing. We're going to come back to power next semester, but power is just the rate at which energy is transferred or work is done. So it's just a rate of usage, kind of like velocity was a rate for displacement. Power is a rate for energy. So we can think of it as energy over time, or we might think of it as work over time. How fast do you do work, or how fast do you consume energy? The units of power are the watt, and 1 watt, which is abbreviated as a capital W, is equal to 1 joule per second. Where do you see a watt? Have you seen a watt before? On a light bulb, for example. On all electrical appliances, actually, if you look on the back, I might even have it on this. If you look on the back of an electrical appliance, it'll have what is its power rating. That is, how much energy does it use. So on all of your electrical appliances, like for example, your dryer might be, I don't know, a couple thousand watts. Your light bulbs are anywhere from 5 watts to 150 watts. A little radio uses about 50 watts or so. It just says how much energy does it consume per second. How many joules per second does it consume? Well, we'll talk about that in an electrical framework next semester. But it comes up sort of embedded in a homework problem. But if I want to find the power done, it's just the energy or the work over time. And we'll see it in some of the quicker questions as well. Let me just review this chapter, sort of all the new stuff that we've seen in this chapter, and then we'll do some more of the clicker questions. Have we done any of them yet for this chapter? We did a few, right? We'll go back and wrap those up. let me just sort of review everything that we've done, because we've had a few new things. So we had work was force dotted with the displacement, all right, which is also the same as the magnitude of the force times the cosine of the angle theta. So work is the dot product of F dot D. And remember on the dot products that I dot I is equal to 1, J dot J, K dot K, those are equal to 1. But I dot J I dot J, for example, is equal to 0. And you can think about it in terms of this cosine theta, that for these the angle is 0, for these the angle is 90, and cosine of 90 is 1. When I have a force and a displacement that are anti-parallel, they're in opposite directions, then that's a negative, because the cosine of 180 is -1. We also had the work done by the gravitational force gives us our potential energy, that's mgh. So if I move an object with relation to the Earth's surface or the gravitational field, it increases its energy, or its potential for motion. Kinetic energy is 1/2 mv squared. That's just the energy of motion. The conservation of energy just says that the initial energy equals the final energy. And when we're talking about conservative forces, this just means that our potential energy plus our kinetic energy equals our potential energy plus our kinetic energy in the initial and final states. And that applied for gravitational potential energy and for elastic potential energy. All right, for gravitational potential energy is mgh. For PES, that's 1/2 kx squared. And then also what we just did is that when I have a positional dependent force, that is when my force changes with the position, then the work done by that force is equal to the integral of F dx. That's when F is dependent upon x. Or when F is dependent upon x. And then finally, the definition of power is just work or energy over time. So we have more equations than we've had in previous chapters. I mean, up till now, we've really only had, 3 or 4 equations that we've been batting around. But now we're starting to get more. All right? When we move into a later chapter, I think chapter 7, I give you guys an equation sheet when you get a lot more equations. But I think for now, y'all should just be able to know these. All right? Y'all good with that? Yeah? Well, let's do a few more of these clicker questions. Okay. We're going camping this weekend because it's fall break this weekend. So we're going camping. Looks like good weather. Huh?
For us, it's next week for elementary.
My kids are off school, so I'm taking off early on Friday. Huh?
Where are you going camping?
Fountain Blue. Hopefully we're gonna get spot number 97. That's our favorite spot because it's sort of away from everybody, and you can. They have like a pull-in spot, but then you can go back into the woods and set up like 50, 100 feet up into the woods. So it's like you're out in the middle of nowhere. But
Tent, all that stuff.
tent camping, yeah. That RV business, that's not good. That's not camping. That's
You want something a little bit less
house on
quaint?
wheels, huh?
There's something a little bit less quaint somewhere. There's something called Lincoln Park in the middle of Lincoln campsite in the middle of somewhere in Mississippi. It's really nice. It has this cool lake that they allow you to go swimming in as far as you want, and they have boats
Okay.
outside of it where you can like leave out and make people hydro slide.
Oh,
It's a
Lincoln Park?
And there's huge area. I wish Camp Salmon was still open.
Yeah, I haven't heard of that.
Camp Salmon is.
Oh, that's the Boy Scout Park.
Yeah, the Boy Scout Park that closed down recently.
Yeah.
Because of Katrina, and they were too lazy to pick up all the trees and fix everything.
Let's get some Boy Scouts out there. All right.
use chainsaws to chop down trees.
Right, right. It's gonna be the trimmed down version. Y'all remember where we left off?
We try and remember when we see it.
Yeah, so if you see it, I'm pretty sure we did all of these.
Did 12 of them.
Well, now I'm on a different one. This look familiar?
Did the
And this?
last one.
We did this one.
We did that.
Yeah, we did.
I don't remember that. No.
Okay, this is the trimmed down version. Let's pick up here. All right, two paths lead to the top of a big hill. One is steep and direct, while the other is twice as long but less steep. How much more potential energy would you gain if you take the longer path? That's gravitational potential energy. So I have two paths up a mountain. One path goes straight up the side of the mountain, and one path takes a more circuitous route up the side of the mountain, which is giving a greater change in potential energy. I'll stop at 50.
There was something really funny in one of my biology classes. We were doing some clear questions after.
Yeah.
Question, it says how much more potential energy.
Right.
So that's extra energy.
What do you mean?
I mean, like the A said the same should be twice like
Uh-huh.
A.
Well, the answer, I'm sorry, what are you asking?
More potential.
Uh-huh. Which path would you gain, would you have the greater change in potential energy? For which path would you have the greater change in potential energy?
The same. I just didn't.
Oh, you didn't get it in? All right. Nobody click. Okay, can I trust you? Look, you're ready to go, aren't you? All right, go ahead. You just wanted to click in? Oh, come on. Everybody click in again. For crying out loud. You get in, Mark? Okay. All right, the answer is A. Oh, y'all did better on the second one. That's good. All right, remember the potential energy, the gravitational potential energy is just dependent upon the change in height. So you have the same change in gravitational potential energy. Okay, how does the work required to stretch a spring 2 centimeters compare with the work required to stretch it 1 centimeter? Stop at 30 seconds. Yeah, we're gonna take our bikes actually to Fontainebleau. You ever been on the St. Tammany Trace? You have. It's nice. All right, 4 times the work. That's right. C is the correct answer. The reason is that the elastic potential energy is 1/2 kx squared, and if I double my x, that's going to quadruple my potential energy because that x is squared. All right, so remember that quadratic relationship. So if you put twice the work, you probably just forgot the squared, right? Mass attached to a vertical spring causes the spring to stretch and the mass to move downwards. So I have a spring here, but then I attach a mass to it, and it goes down like that. What happens to the spring's potential energy and the gravitational potential energy of the mass? Stop at 55. That's right. B is correct. Because x is increasing, that is the elongation of the spring. So the potential energy of the spring is increasing, 1/2 kx squared. But the gravitational potential energy, H, is decreasing. So H has some value here, but then it has a lower value here because it's closer to the ground. So my gravitational potential energy, mgh, is actually going down. So this is increasing, but the gravitational energy is decreasing. Three balls of equal mass start from rest and roll down different ramps. All ramps have the same height. Which ball has the greater speed at the bottom? What?
Question.
Yeah.
Is the ramp a frictionless surface?
We can say they're all frictionless, yeah.
I think so.
Rolling friction is very small, so we'll say it's negligible. That's why I use bearings, right? Because rolling friction is very, very small. Stop at 45. All right, B is right. All right, so I'm starting at the same height for all these. And so they all have the same amount of gravitational potential energy, mgh, because h is the same for all of them. And when they get to the bottom, all that potential energy will be converted into kinetic energy, which is going to be 1/2 mv squared. So at the bottom, they're all going to have the same kinetic energy. I want to know what you're thinking the minute you put A, is that A is going to accelerate at a greater rate. And that's true, A will accelerate at a greater rate than the ball at C, but it's also going to take what, more or less time to get to the bottom? It's going to take less time. So it'll accelerate at a greater rate, but at a lesser time. So its final velocity will still be the same as ball C. Now it might get there first, but or will get there first, but they'll still be going the same velocity at the bottom. What happens if friction is not negligible? So let's say that friction, we're going to do it as another question. So just this question all over again, but let's say that you do have friction, that it's relevant. Which one will be going faster at the bottom of the ramp? So frictional forces are relevant. Stop at 25. 25. Very good. A is going to be going faster because that frictional force has less time or less distance to act over, and so it takes less energy away from the ball. So A is the correct answer. Box is sliding on a frictionless flat surface, runs into a fixed spring, and presses the distance x to stop the box. Stop at 50. All right, look, so I have an initial energy, which is all kinetic energy, 1/2 mv squared. And then all that energy is converted into elastic potential energy, 1/2 kx squared. And I want to know if I double my velocity by a factor of 2, what's going to happen to my x? By how much is it going to increase? If I double v by a factor of 2, how much will x increase? Let's try it again. Stop at 20. Are you serious? What did that be before?
What?
I'm doing that right, aren't I? Am I doing it right?
Oh, I see.
Yeah, I'm doing
We're
that
reading
right.
the question wrong. We're thinking how you were saying it. You were saying how much would the string compress and we were thinking in terms of 1 and 1, in which we would think if we double one, it'll be double for the other, twice as much for the other.
Oh, no, I'm sorry. It is twice as much.
Oh.
Yeah, I'm sorry. I guess I was just brain farting. I'm sorry. Yeah, so it is D. Okay. All right, so we did improve. All right, good. I'm sorry. Yeah, so it is D. That if I increase V by some amount, it increases X by the same amount. Because V and X are linearly proportional. They're squared, but they're both squared. Sorry about that. Mike applies 10 newtons of force over 3 meters in 10 seconds. Joe applied the same force over the same distance in 1 minute. Who did more work? We're almost done. Stop this at 30. All right, good. They both did the same work, same force, same displacement, so same work. Just a couple more. Mike did 5 joules in 10 seconds. Joe did 3 joules in 5 seconds. Who produced the greater power? Remember, power is just work over time. Stop at 30 seconds. Very good. Joe does 0.6 watts. Mike does 0.5 watts. It's just work over time. And finally, I'll just give you the answer to this, but a kilowatt is energy per time, and when you multiply it times an hour, that's time, you just get energy. All right, so when energy charges us for kilowatt hours, that's actually charging us for energy, not for power. They don't care about our rate of consumption, only how much we consume. We'll see that again next semester. All right, you all have a great day.